Okay, in this first video on magnetism, we're going to start off by looking at flux and flux density, and then we'll finish off by looking at MMF, magnetomotive force, which leads on to our field strength, magnetic field strength. Okie dokie, let's get going. So if we look at a simple bar magnet to start with, then what we've got is emanating from the North Pole is we've got some imaginary lines of force that go out from the North Pole and to the south, and these imaginary lines are called magnetic lines of flux. And the unit of these magnetic lines of flux is the Weber, and we can abbreviate that down just to WB. So they are imaginary, but it helps us to understand what's going on with the magnet. So if we take two magnets and we put them next to each other and put both norths next to each other, we could do the same with if we put both souths. What they're going to do, we already know from messing around with magnets that the magnets are going to repel each other. Why they're going to repel each other? Well, we can see that using the lines of flux. So we end up with something like that. That picture there that illustrates that the lines of force are acting to repel each other. Okay, so let's put this all together with a bit of a calculation. So we can say if we've got a strong magnetic field, then we can define that using the realms of flux density. Flux density is the magnetic lines of flux, what the value are, what they are in Webers, divided by the area in meters. And the answer then, the unit for flux density is the Tesla D. Okay, so if we take this this is an example. We've got magnets, and it's got the flux lines 80 microwebers, and the area of the end of the magnet. Oh, sorry, not the area of the end of the magnet. The size of the end of the magnet, 3 centimeters by 2 centimeters. So if we want to know what our flux density is, then let's pop all that into our equation. So we know that P is equal to that over area. So we know that that's 80 times by 10 to the minus 6 Webers, and our area. Okay, so we need to convert this. So we've got our answer in meters. So 3 times by 10 to the minus 2 times by 2 times by 10 to the minus 2. So using the centi, so we've got numbers directly into meters straight away. Gives us an answer of 133.3 milliteslas. Not sure what happened there, but okay, we just recovered it. Okay, and they're all just like that. There's nothing to it. So what I want to do is now look at magnetomotive force, MMF. So if we create a magnet, we're going to create a magnet by passing a current through a coil of wire. Okay, so we can look at what that generates. So our MMF is equal to number of turns multiplied by the current, and the unit is the ampere, so we just use A. Okay, so a lot of the time we actually we don't want the magnetomotive force, we actually want the magnetic field strength. So magnetic field strength H is given by H is equal to number of turns on a magnet multiplied by the current flowing through it divided by L. So where L is the length of the flux path. And the units for magnetic field strength H is the ampere per meter. Shall we have a little example? Okay, so take this example, mean diameter 15 centimeter ring. We've got 2,500 turns of wire wrapped around it carrying 2 amps of current. So we need to know what the magnetizing force is. Oh, spelling mistake there. So the first thing we're going to do is work out what L is, and then we'll take it from there and put the numbers in our equation. So we get an answer of 10, 6, 10, ampere meters. Okay, so some of you might be looking at this and going, well, that looks a bit clumsy. Rather than writing 15 pi times 10 to the minus 2, but if you try and type that into the calculator, it won't work. So 15 times 10 to the minus 2 times pi, that will work if you type that into the calculator. That's why I wrote it that way around. Okay, rambling now, so I think that's the end of the video.